The James Webb Space Telescope, often referred to as JWST, has dramatically changed how we look at the universe. In many ways, it has upset the apple cart of modern astronomy. For decades, scientists relied on existing telescopes and spacecraft missions to develop theories about the origins of the universe and the nature of celestial objects. However, the astonishing precision of Webb has forced researchers to reconsider many of their assumptions. In fact, there is now a growing realization that astronomy textbooks may need to be rewritten from the ground up. One of the most surprising cases has been the new insights into Pluto. When the telescope directed its ultra-sensitive instruments toward this distant world, no one was prepared for the revolutionary images and data that came back. They were not merely clearer than before, they were transformative. Pluto has always fascinated astronomers. It is a small, icy world that for decades was little more than a blurry speck at the far reaches of our solar system. Even after NASA's New Horizons mission completed its historic flyby in 2015, revealing Pluto's complex surface and heart-shaped feature, countless mysteries still remained. New Horizons provided a fleeting glance as it sped past, but Webb, with its powerful infrared sensors and high-resolution imaging capabilities, has given humanity a far more detailed and sustained view. For the first time, we can see Pluto with clarity that was once thought impossible, and the implications are staggering. Once regarded as the ninth planet in our solar system, Pluto continues to capture the imagination of scientists and the general public alike. Situated in the Kuiper Belt more than 3.66 billion miles away from Earth, this dwarf planet has always been a challenge to study in depth. Traditional telescopes, even the legendary Hubble, offered only vague glimpses of its surface and atmosphere. But Webb has completely changed the situation. Thanks to its massive 6.5-meter gold-coated mirror and its vantage point beyond Earth's atmosphere, it can capture faint light with unprecedented precision. When Webb's gaze fell upon Pluto, the result was nothing short of breathtaking. Suddenly, scientists were looking at features, textures, and atmospheric conditions in a level of detail previously unimaginable. What makes Webb's achievement even more remarkable is how it observes the cosmos. Unlike telescopes that primarily collect visible light, JWST is designed to detect infrared radiation. This gives it the ability to see heat signatures and variations in temperature and composition that optical instruments simply cannot detect. In the case of Pluto, this means Webb can peer through its thin, tenuous atmosphere and track changes in surface ice, revealing signs of potential geological activity. The latest images released jointly by NASA and the European Space Agency are stunning. They display intricate details of Pluto's surface, including nitrogen ice plains, mountainous terrain, and even evidence of possible seasonal changes within its atmosphere. One of the most dramatic revelations concerns Sputnik Planitia, the enormous heart-shaped region that dominates Pluto's surface. This icy plain, composed mainly of nitrogen, was first observed during the New Horizons flyby, but Webb's infrared sensitivity now provides depth, texture, and contrast that were invisible before. Variations in brightness across this vast region suggest ongoing surface processes, such as sublimation and deposition of nitrogen ice. These findings hint that Pluto may still be geologically active, despite its small size and frigid environment, something that once seemed improbable. Webb's data has also revolutionized the study of Pluto's delicate atmosphere. Comprised primarily of nitrogen, with smaller amounts of methane and carbon monoxide, Pluto's atmosphere is thin, cold, and fragile. Yet in the infrared spectrum, subtle changes in temperature and composition become far more noticeable. This enables scientists to trace shifts in atmospheric pressure and thermal structure over time. Since Pluto takes 248 years to complete a single orbit around the Sun, its seasonal cycles are long and complex. Webb's ability to track these subtle atmospheric variations is providing invaluable clues about the planet's ongoing climate changes. But Pluto is not alone. It has a family of moons, and Webb has given us fresh insights into them as well. The largest, Charon, has long been of particular interest. Roughly half the diameter of Pluto and locked in synchronous orbit, Charon always shows the same face to its parent world. Webb's imaging revealed intriguing surface compositions on Charon, including frozen ammonia and possibly complex hydrocarbons. These discoveries suggest that Charon's crust may have undergone significant geological transformations in its history, challenging the assumption that such small worlds are inert and unchanging. Beyond Charon, Webb has also turned its instruments toward Pluto's four smaller moons, Styx, Nix, Kerberos, and Hydra. These irregularly shaped bodies have been notoriously difficult to study because of their size and distance. Yet Webb's precision has allowed scientists to refine their orbital measurements, make better estimates of their surface compositions, and speculate more confidently about their origins. Collectively, these findings contribute to a more comprehensive understanding of the Pluto system as a whole, shedding light on the dynamic interactions between a dwarf planet and its companions. One of the unexpected outcomes of Webb's Pluto observations is the renewed debate about its planetary status. Since 2006, when the International Astronomical Union reclassified Pluto as a dwarf planet, controversy has raged in both the scientific community and popular culture. The new data complicates this debate even further. The richness of Pluto's geology, atmosphere, and potential internal ocean suggests that it shares many traits with recognized planets. Some astronomers argue that Pluto deserves reinstatement as a full-fledged planet, given its complexity and dynamism. Webb's observations add weight to this argument, showing that Pluto is far from a lifeless rock at the edge of the solar system. Equally important is how Webb's clarity highlights the scientific significance of studying the Kuiper belt in general. Pluto is only one of thousands of icy bodies orbiting the Sun beyond Neptune. With Webb's help, researchers can now target other Kuiper belt objects, KBOs, such as Eris, Makemake, and Haumea, along with still undiscovered bodies. Each new observation contributes to the larger puzzle of how the solar system formed and evolved over billions of years. Unlike the Hubble Space Telescope, which excelled primarily at capturing visible and ultraviolet light, JWST's infrared capabilities enable it to peer through cosmic dust, detect faint heat sources, and reveal objects invisible in visible light. This makes it uniquely suited for studying distant, cold worlds like Pluto. While Pluto emits little visible light, it shines brightly in the infrared spectrum, making it a perfect target for Webb's instruments. Equally impressive is the sheer engineering achievement behind capturing these images. Pluto is not only distant but also relatively small and in constant motion. Webb's fine guidance sensors had to operate with extraordinary accuracy, compensating for both the telescope's movement and Pluto's slow drift against the starry background. The fact that Webb produced such detailed imagery demonstrates not only its versatility but also its robustness as a scientific instrument. This versatility is one of Webb's defining strengths. It is equally capable of looking billions of years into the past, capturing the faint light of the earliest galaxies, and turning its attention to icy worlds within our own solar system. By bridging these two extremes, Webb is helping humanity construct a more complete narrative of the universe, from its very beginnings to its current state. This adaptability also raises exciting possibilities for future research, including detailed studies of Triton, Neptune's mysterious moon, as well as other large Kuiper belt objects. Of course, Webb cannot answer all questions on its own, but it frames them in sharper focus. Its Pluto observations raise tantalizing mysteries. Does a hidden ocean lie beneath Pluto's frozen crust, as suspected for moons like Europa and Enceladus? What drives its apparent geological activity in such an inhospitable environment? Could cryovolcanoes be actively reshaping the surface by releasing volatile compounds from the interior? These questions will guide future missions and studies, but without Webb, they might never have been asked in the first place. Another fascinating outcome is the opportunity for comparative planetology. By examining Pluto alongside other icy worlds, scientists can identify common features and significant differences that reveal broader processes in planetary science. For example, comparing Pluto's nitrogen cycle with Triton's could help us understand how similar mechanisms operate across the solar system. Studying organic compounds on Pluto